Now, we've been using this term significance level for a bit now, and setting it to different values like 0.05 and 0.1. But it's a very important concept to understand what that means, what it implies about the properties of the hypothesis test, because it's telling us, at least in one sense, in one dimension, how likely we are to be drawing correct inferences from our hypothesis test about the underlying population. So let's go to here. So what is the significance level about? Okay, so we'll describe it for an upper tail test, but then the concept is basically the same, just a mirror image in the lower tail test. Okay, so for an upper tail test, this was our setup. Okay, so we had hypotheses that the mu was equal to some given number against the alternative that the mu was greater than that number. So we calculated the test statistic, and we'll discuss it in terms of the critical value decision rule. It's a little bit easier. So the decision rule is that we will reject the null hypothesis if this statistic is far enough into the upper tail of the distribution such that it gets past this critical value, where this critical value is chosen such that the probability that the t-distribution is above that critical value is equal to this given alpha. Okay, so this is our critical value, again with the two subscripts, and this thing here is referring to the t-distribution with n-1 degrees of freedom. Okay, so those steps there describe what we do. Okay, we want to test these hypotheses, so we calculate this t-distribution and then make a decision. Either we reject the null hypothesis if this condition holds, or we do not reject the null hypothesis otherwise. And so we've been specifying this alpha to be something like 0.05. But what's going on with that? What is that really measuring? You can see in the pictures, it is giving you kind of this cutoff out in the tail of the distribution somewhere. So it's kind of acting as a cutoff for saying when are we far enough into the tail. It's important to be aware of what this means in a probabilistic sense as well, because clearly it is a probability, right? It is the probability of the t-distribution being greater than the critical value that we're using. Alright, now this statement here has been hanging around in all of our specifications, and this is important to understanding what the significance level is really about. So we've been treating the t statistic as being approximately t-distributed with n-1 degrees of freedom when the null hypothesis is true. Okay, this is the important thing. So if this m is the correct value for mu, then this t statistic that we're calculating is the same thing as taking the x bar minus the mu. Okay, we spent a couple of lectures to set up the fact that this ratio here, its sampling distribution is approximately t. Okay, the x bar is approximately normal, and then we put the sample standard deviation down here, which adds that little bit of extra noise and turns the normal distribution into a t distribution. All of which is assuming that the null hypothesis is true. Okay, so this m really is equal to mu, and that distribution works. So this probability statement that we're talking about here is one that we've worked out under the condition that the null hypothesis is true. So you can think of the probability that we're working out for this critical value is something which is relevant when the null hypothesis is true. So notice what this decision rule is telling us. We're rejecting the null hypothesis if the t statistic is above this critical value, where the probability of being above this critical value is equal to alpha if the null hypothesis is true. Okay, just piecing all of those pieces of logic together there. Okay, if the null hypothesis is true, the probability of our t statistic being above our critical value is equal to alpha, a number like 0.05. In other words, and this t statistic being above the critical value, that corresponds to rejecting the null hypothesis, just to be even clearer about that. Okay, so what does all this mean? This is saying, so again, going from here, through here, and back to if the probability is being calculated if the null hypothesis is true. So if the null hypothesis is true, the probability of rejecting the null hypothesis is equal to alpha, so 0.05. All right, but, okay, you might stop there and think, wait a minute, I don't want to do that. If the null hypothesis is true, I don't want to reject the null hypothesis. That's the wrong decision to make. Now, having some probability of making a wrong decision is actually, well, practically unavoidable in these situations, because we only have a sample. We don't have perfect information. We don't have all of the data in the population. We only have a small subset of it in our sample. So we don't have perfect information, which means inevitably any decision-making process that we set up on the basis of a sample will have the possibility of some wrong decisions, of some errors. And one of the important things about setting up these methods of statistical inference is to start to understand, well, first of all, define exactly what these errors are, and then to try to quantify what are the probabilities and try to control what the probabilities are of making these errors. And in particular, to try to ultimately make those errors as small as we can. So, the way that we do these hypothesis tests has, now that we see this sequence of logic here, has built into it an error, the probability of an error. Okay, so if the null hypothesis is true, the probability of erroneously rejecting it is equal to alpha. Okay. We call this a type 1 error. There are going to be two types of errors. So this is a type 1 error, is the decision to reject the null hypothesis when it's true. Okay, so that's a wrong decision, obviously. If the null is true, we reject it, we've made a mistake. And this significance level, this value that we set to be a small number, notice, so we don't set the probability of making a type 1 error to be like 0.9 or something, that would be disastrous. So we set the significance level to be 0.05 to try and, or 0.0, or 0.01 or 0.1 or some number like that, so that the probability of making this type 1 error is there because it has to be there, but to try and make it not too large, I guess. So there's some arbitrariness associated with this choice. Okay, so the choice of the 0.05 is to say that we're happy to live with the possibility that the null hypothesis may be true, but we end up rejecting it, 5% of the time. Okay, so that's what the significance level is saying. It is controlling the probability of making a type 1 error. So whenever we set the significance level of a test, that's what we're setting. And then in any particular application, if you're particularly concerned about making a type 1 error, then you might want to think carefully about what significance level would be appropriate. So this area, this probability that we've been talking about, illustrating all of it, so this is the probability of a type 1 error for an upper tail test. Okay? Because this distribution, this t-distribution, centered at 0 here, this t-distribution is the distribution which is correct when the null hypothesis is true. Okay? And if the null hypothesis is true and we reject the null hypothesis, that's a type 1 error. So this is the probability of a type 1 error here. Okay, so these distributions that we've been drawing are always the distributions that hold when the null hypothesis is true. When the null hypothesis is not true, when the population mean is equal to some other value, then this distribution is different. It moves someplace else. Okay? We'll talk about that later on. We don't need to talk about that to implement the hypothesis test. That's a different topic. For the lower tail test, it's exactly the same story, right? We just move everything down into the left-hand end of the distribution so that the probability of the type 1 error is 0.05, and that happens to occur in the lower tail of the distribution. But really nothing of the logic that we've just been describing is any different. So again, the significance level is controlling the probability of wrongly rejecting the null hypothesis. All right, with that information in hand, so that's important. That's an important point of understanding about what these hypothesis tests are doing and what the significance level means. Okay? Now it's also helpful just to have that information in hand when we set up a two-tailed test for a mean as well. So in this case, we have the same starting point, which is a simple random sample from some population with a population mean mu that we want to test a hypothesis about on the basis of the sample mean, so same stuff. The hypotheses now take this form, so that the mu is not equal to whatever the null value is. Okay, so it's two-tailed because we're interested in both deviations above m and below m. Either one we're interested in detecting. So basically we want to combine in some way the upper tail and the lower tail tests to form this two-tailed test. We continue to base the test on the t statistic, and the x bar minus the hypothesized value here divided by the standard error, and it continues to be true that if the null hypothesis holds, if mu really is equal to m, then this t statistic has a t distribution. So you see for all of the tests, this bit is the same. You calculate the same statistic and you use the same distribution to make your probability calculations. Whether those are p-values or critical values, you'll get them from the same distribution regardless of the alternative hypothesis. Okay? So this much stays the same, but then your decision rule is different depending on what is the form of the alternative hypothesis. So in this case, the decision rule for a two-tailed test, at least intuitively, is going to be that we reject the null if the t-statistic that we calculate is far enough into either tail. If it's in the far enough into the upper tail or into the lower tail, then we will reject the null. Okay, so in the one-tail tests, upper or lower, we only ever check for deviations in one direction, whereas now we're checking for deviations of x bar from m in either direction. If we don't find them, then we do not reject the null. Alright, how are we going to set up a decision rule for this? Well, basically we set up a decision rule. We'll start with the critical value form. It's a bit more intuitive in this case. The critical value form says we're going to reject the null hypothesis if the t-statistic that we calculate is greater than some positive critical value, or if it's less than some negative critical value. So this one here is capturing the idea of the t-statistic being in the upper tail of the distribution, and this one is capturing the idea of the t-statistic being far into the lower tail of the distribution. So these are critical values in exactly the same way as we had critical values for the upper and lower tail tests, but they're just slightly different in one respect, which is, notice we've got this alpha on 2 thing here. So we used to have the critical value being t alpha, comma, n minus 1 for the degrees of freedom. But now we've got alpha on 2. And the reason for that is we're kind of breaking up our rejection region into two parts. And so we're making the size of the rejection region half as big in the upper tail and in the lower tail. That's what that alpha on 2 is doing. We'll see a picture in a minute. This critical value here, this definition of the critical value that we're using in here is not new. This is exactly the same definition as the critical value we've been using all along and can be calculated in exactly the same way we've been using all along. So using the tdist command in Excel or looking up in the tables, the only difference is if your alpha is, let's say, 0.05, then you need to divide it by 2 in these kinds of statements. Having these two rejection rules, or two parts to the rejection rule, is fine. There's nothing wrong with that, but we can kind of just combine it into one like this. It's a little bit more convenient and it focuses on what's important. If the absolute value of the t-statistic is greater than greater than the positive critical value, then we will reject the null. So you can see that this is looking at the positive end. So if the t-statistic is positive, then the absolute value is positive. And then if we're looking down at the negative end, then if this t-statistic is very large and negative, then if we take its absolute value, it becomes positive. If we take the absolute value of this negative critical value, it becomes positive. So this absolute value decision rule captures both of those. Okay, so it's just a more convenient way. It's telling you that we're not interested. It's informative because it's saying we're not interested in the sign of the deviation from m. Whether it's positive or negative, we don't care. We only care whether the absolute difference is large. decision rule can be expressed in terms of the absolute value quite conveniently like that. And it's exactly equivalent to that, of course. Alright, here's how you would calculate the t statistic. So nothing new there. Okay, the t inverse is what we've seen before. The 1 minus alpha on 2 is the same as what we had the 1 minus alpha before, but now we've got alpha on 2. Now, if the null hypothesis is true, okay, so let's just go back and reinterpret the significance level that we're talking about here. So we've defined ourselves a test here, and I've kind of said it kind of seems like it's a sensible idea to put alpha over 2, maybe or maybe not. Let's see how that is expressed in terms of the significance level for the test that we've defined. So if the null hypothesis is true, then this t statistic is t-distributed, and therefore the probability that this t statistic is above this critical value, so we're referring back to here, is going to be equal to alpha on 2. Okay, so this probability statement here comes directly from this probability statement here. So the definition of this critical value is that the t distribution falls above this critical value with probability alpha on 2. Okay, if the null hypothesis is true, then this t statistic here has a t distribution. So these two probability statements become the same thing when the null hypothesis is true. Okay? So when the null hypothesis is true, t is at least approximately t-distributed. Exactly the same thing holds in the lower tail as well. Just flip it around to the lower tail and we get alpha on 2 in the upper tail, alpha on 2 in the lower tail of the distribution, and then you can see when you put those together, the probability of either of those things happening, so we're referring back to this decision rule now, the probability of this happening or this happening is equal to alpha if the null hypothesis is true. Okay, so this idea of halving the value of alpha in the upper tail and in the lower tail turns out to provide us with a two-sided test or two-tailed test with an overall significance level which is equal to alpha. Okay, so when we say we want a 5% test, for example, that means we want to allocate 2.5% into the upper tail and 2.5% into the lower tail. Here's how the picture of that looks. Okay, so if we want to do a two-tailed test at the 5% significance level, then we would allocate 0.025 of the probability down here and work out that critical value, and 0.025 down here. Okay, so the exact value of this critical value will depend on the degrees of freedom. Okay? It's approximately 2, between 1.96 and 2 most of the time, depending on the value of n for that number. But you can see, anyway, the main point is to understand with the two-tailed decision rule, we're going to pick this critical value, which is kind of a mirror image of this critical value, and we are equally distributing some of the significance level to here, so half of the alpha here and half of the alpha there. Alright, let's have a look at an example of all of that in action then. And we'll return to what we originally talked about as an example of a hypothesis test, which is the IQ scores for the children with the cochlear implants. The data set looks something like these are the first few IQs for these kids, and we're interested in testing whether the mean IQ for children with these cochlear implants differs from the mean IQ for the general population, which is standardised to be 100 in IQ tests. So in that question, it's fairly succinct, and the mu, the population mean we're interested in here, is the mean IQ for the children with the CRs. Okay, we know what the mean IQ is in the general population. We want to know about the mean IQ for this particular group of children, which may be different, we're not sure. Okay? And the question says differ, and that's important as well. So we're not just interested in the possibility that the IQs are higher or lower on average, just any difference is of interest to us, and therefore that is telling us, that word there is telling us that we want a two-sided alternative for our hypothesis test. Okay, so the null value is 100, so we always have our equals for the null value, which says that the mean for this population of these children is equal to 100, same as for the general population, and then the alternative is that it doesn't. We're looking for evidence of difference here. here are the statistics. We have a total of 90 kids in this sample, and the average IQs, if we work out all of those, is equal to, we'll take the average of all of those, 105.22, standard deviation of 12.53, and the t-statistic then works out to be 3.95. So they're kind of simple calculations. There's probably no need to stop and show you those right now. I think you could reproduce those, and you can. The spreadsheet will be there, and you can grab that spreadsheet and reproduce those calculations. It'd be a good exercise, just to make sure that you're keeping up. Now, how do we set up the hypothesis test? So here we're going to grab the required critical value to do the 5% test. Now notice in this question, if we return back up here, nothing is specified about the significance level, so we'll use the 5% significance level. So that's what this means. So the default is alpha equals 0.05 if you're not told otherwise. So that's what we do. Now we're implementing this. Let's just go back to this notation here to show where this is coming from. We want to do this kind of thing. The critical value is t, alpha on 2, comma, degrees of freedom. So that we've been told the alpha, we figured out now the alpha is 0.05. Okay, so this is what we're looking at here. So alpha on 2 is 0.025, and the Excel command is therefore 1 minus alpha on 2, which gives us 0.975, and there's a total of 90 kids, and so the degrees of freedom is n minus 1, 89. And that returns to us a critical value of 1.987. And again, I encourage you to just go into the spreadsheet and just type that in, just type that much of it in, and make sure that you get that number out as a result. In fact, pause the video and go and do that and come back. So with the two-tail test, I guess the important thing to remember is when you are doing it at a 5% level, you have to remember to, for a two-tail test, to use half of the significance level here to work out this critical value. That's the additional thing to remember with this. Then that's it. If you want to implement this using a critical value, it's simple now. We've got the t-statistic, which is 3.95. In this case, we have a rejection in the upper tail. Okay, so this t-statistic is greater than the positive of the critical value. In general, we put kind of like an absolute value. So if we got a t-statistic, let's suppose things turned out and we had, like an x bar of roughly 95 here, let's say, and the t-statistic therefore turned out to be minus 3.9, then we would also reject the null because minus 3.9 is greater in magnitude than this critical value here. Okay, so 3.9 rejects the null because it's greater in magnitude, and minus 3.9 would also reject the null. So we're only interested in the magnitude of this statistic. It happens to be positive in this case. Deviations, so large values, either positive or negative, large magnitude values will reject the null in a two-tailed test. So in this case we do reject the null and find that the difference between the average IQs for these cochlear implant kids is in fact statistically significant at the 5% level. You can look up a critical value from the table, and again the only difference from looking up critical values before is that you need to remember to take the alpha on 2. So if you want to do a 5% test, then look up 0.025, the alpha on 2, in the table of critical values. And so as long as you've got that correct, then you just got to find the degrees of freedom, which in this case we had 90 kids. So degrees of freedom 89 is close enough to 90. And there's the critical value 1.987, which is what we calculated from Excel as well. So either way, make sure you get the same critical value. Now, what about a p-value form for the two-tailed test? So in practice, I might just mention that most hypothesis tests these days do get carried out using p-values. This is an important thing to know about, that they are generally more convenient. Now for a two-tailed test, the form of the p-value just takes a little bit of extra working out, I suppose. So let's return to the critical value decision rule first, and we'll derive the p-value decision rule from this one. Okay, so the critical value decision rule says we'll reject the null if the absolute value of the t statistic is greater than the critical value. Okay, when the critical value satisfies this probability statement. So kind of what this is saying, what this is saying is if the t statistic is large enough in magnitude to be right out into the tails of the distribution, then we reject the null. Now when we want to translate something about a t statistic into something about p-values, and we want to talk about probabilities, we want to talk about areas under the curve. So this is the key point here. Okay, so if the t statistic is a long way out into the tails of the distribution, then the probabilities are going to be small. Okay, so what we have here is that the probability of this t distribution being larger than this critical value is equal to alpha on 2. Okay, that's how we've chosen, that's the definition of this critical value here in the first place. Okay, that's been defined to satisfy that probability statement. If the t statistic that we've calculated in absolute value is further out into the tail than our critical value, then there will be less probability above that t statistic than above the critical value. Okay, so if the absolute t is bigger than the critical value, then the probability above that absolute t will be less than the probability above the critical value. Okay, it gets reversed around. The further you go into the tails of the distribution, the less probability there is out there. Okay, and that's kind of the key equation right there, really. Now what we do in order to turn that into the final p-value decision rule is to say, well, we've defined this critical value here in such a way as this probability is equal to alpha on 2. Okay, so this blue probability here is equal to alpha on 2. And we could just define, this could be our p-value decision rule right here. We could work out what is the probability of the t distribution being greater than the absolute t statistic and compare it to this alpha on 2. But what's more commonly done is that we multiply on both sides by 2. And the reason for that is purely so that instead of having an alpha on 2 on the right hand side here, which is this probability, we have an alpha. So that's the only reason. So we just want to end up with a decision rule where we are comparing a p-value with the specified significance level of alpha. So multiplying on both sides of this inequality by 2 gives us that. So what that little bit of logic there shows us, those couple of lines, shows us is that if we have a decision rule that says we're going to reject the null hypothesis, if the test statistic in magnitude is greater than a critical value, which is defined to follow this probability statement up here, then that is exactly the same thing. It makes the same decisions in every case as a decision rule which says we're going to reject the null hypothesis if the p-value is less than alpha. But the p-value is defined in this very particular way. Okay, so this is the two-sided p-value, if you like. Okay, so the definition of the two-sided p-value is twice the probability of the t distribution falling above the absolute t statistic that you calculated. Okay, so to calculate this p-value, you calculate your t statistic, take its absolute value, so if it's negative, throw away the minus sign, and then work out this probability using the tdist command, and then multiply by 2 for the two-sided test. And that's your p-value that you would compare to the 0.05. Alright, here is how this works in action in Excel. So all the way down to here is the same, right? We've already calculated this 3.95 is the t statistic, and now we want to go from this to a p-value. So it goes like this. Here's the command. Now Excel actually has built into it a two-tailed t-distribution command. So it handles the 2 times bit for you. So the command is as follows. The p-value is the tdist, two-tailed, 2t. Now I've put in this absolute value here just as a reminder that in general, whatever that t statistic is, we want to take its absolute value. Now of course this is a positive number, so we didn't need to take it, okay? So that in this particular case, you wouldn't bother with the absolute value. But if this were a minus 3.95, then you need to remember to take away that minus sign and put in plus 3.95. So I've just put that in there as a reminder that it's important to put in the absolute value of the t-statistic in there. Now in fact Excel will remind you pretty quickly if you do try to put in a negative. So if you worked out like a minus 3.95 and you put in minus 3.95 here, Excel will actually give you an error. It says that that's not an allowed value for the two-tailed version of the t-distribution. So just make sure you've got a positive thing there. There's the degrees of freedom, and in this case the p-value works out to be 0.0002. So that's a long way out into the tails, right? That's a very small area under the curve, under the t-distribution. By the time we get to a p-value, that's that small. So that p-value, that p-value should obviously be less than 0.05, right there. That p-value, that inequality is the wrong way around, I'll change that. So the p-value should be less than 0.05, which implies that we would reject the null, and the difference is significant at the 5% level. Which is, again, the same conclusion as we drew using the critical value, the critical value test, as it must be. So you need to know how to use both the p-values and the critical values. So to summarise all of that stuff about hypothesis testing, we've now done, well, basically all of the types of hypothesis tests for a single mean that we need to do. So we've seen one-tail and two-tail tests, how to calculate a t-statistic. There's only one kind of t-statistic. We've introduced the concept of the significance level, which is the probability of rejecting the null when the null is actually true. Okay, so the significance level is the probability of a type 1 error. But you'd add type 1 error to that list there. So the significance level, probability of a type 1 error, you should know what that is. And then we have two types of decision rules that apply to any of these kinds of one or two-tailed tests. So you should know how to implement a test using a critical value, including looking up the critical value from the table if necessary, and also how to implement a test using a p-value. Okay, so there's quite a bit there. I'd advise you to kind of revise over this stuff and reproduce the examples that I've done in these videos. The spreadsheets will be on the LMS, and then obviously practice using the tutorial and textbook exercises as well.